call this a congruence condition. So for all j, it's lambda j minus lambda j plus a is less than or equal to b, only if lambda j plus 1 plus lambda j plus a is congruent to c mod d. So if two parts are at some distance are close enough together, then their sum, along with all of the parts in between, has to be congruent to something mod something. Without going into details, there is reason to stick in the intermediate terms here. Of course, in Capparelli's work, this is just distance 1, so we don't have to, it's just the sum of the two parts, so we don't have to worry about that.
This comes up in Bressoud also.
Yeah. So this sort of thing comes in Bressoud, and so it certainly is suggestive of if you're trying to generalize this is the way to do it, although it never hurts if you're just doing pure experimentation to try it the wrong way and just see what happens, just for the heck of it. Okay, so this is kind of the work that's been done before. Any questions? Okay, so now we can kind of try to put
By the way, maybe I'll say Doron Zeilberger had something to do with the history of this. When Andrews wrote the citation for the Wilf Zeilberger Steele Prize for Fundamental Research, Andrews wrote, this is in the AMS notices, that his proof of Capparelli's conjecture, which Capparelli hadn't quite finished proving at the time, used the WZ method.
Mm-hmm. Yes. So everything is very much interconnecting here. Yes. So we can kind of think to ourselves, okay, now we kind of have this backdrop. What should be going on in our minds? And we're trying to use experimental math to come up with new identities. And so we can think about, okay, so we can, how many parameters can we play around with? So we have a difference at a distance, that's 2 parameters. We have a minimum size of smallest part, and how many times this part is observed here. That's 2 more parameters. And then I see 4 congruence parameters down here. And so what we might think about doing is that we can merely, let's see, I don't care about this. Let's work out. We don't really, so this is suggestive of we can just do some brute force calculations to come up with some size. So what do I mean by that? So methods, brute force calculate. Okay, so let's say you're exploring some parameter space. So come up with minimum and maximum values for all 8 of these parameters. And then you're just going to run through maybe all partitions up to size 15 or something like that. And so you can just kind of brute force calculate and ask for each partition that you come across, ask it, does it satisfy all of these conditions with the given parameter values? And if it does, then you add in a factor of 1 times q to the end. If it doesn't, you don't add in that factor. And so you end up with, so for each one of these, you end up with some start to the generating function for your sum side. So you're going to have 1, so all of these series are going to start off with a 1. We say the empty partition, the partition of 0, satisfies all of this trivially. It makes all the math work out nice. And so then we go up to n equals 15 perhaps terms, or 20, maybe 15 is enough. So go out to 40, whatever values you want. And then we can use Euler's algorithm factor this as a product side. Okay, so Euler's algorithm, and in the interest of time, I don't think I'll go through. I'll describe it too much. You can just kind of treat it. It's not too hard. You can just treat it as a black box. So basically, what it does is that it just recursively calculates. So any write down any series starting with 1 as a unique factorization into something of its product form. Although you aren't, before over there, all of our exponents are always, -1 or 0. Here, we're not promised anything about what the exponents come out to be, but you're guaranteed to be able to do this, and this is not hard to do. And so, what are we looking for? We want congruence classes. So we want this product side to factor so that all, if we're lucky, if everything works out well, these will all be 0s or 1s, and then you will get some sort of periodic sequence. And we see a periodic sequence of 0s and 1s, then that is very, very suggestive that that our product side is going to be the appropriate. That's going to use some sort of congruence classes, and you can do this to as many terms as you want. So at this point, let me go ahead and turn on the computer, and let's actually play around with this a little bit ourselves.
Matt, you could have used a different set of factors, for instance, cyclotomic polynomials in the denominator there.
Uh-huh.
You could have run through all the cyclotomic polynomials and looked at their exponents, and that would give you a different set of, instead of the A's, you get the C's and other sets.
Right. I guess the question then is, so would you end up getting a partition?
It'd be a linear combination of the A's, but it might be more obvious.
Yeah, but I think in detail it will be more complicated.
Sometimes.
Yeah.
While the screen is coming down, I can answer your previous question. So Kailash Mishra and Evan Wilson, Evan Wilson is a lecturer here. They have some identities where you look at only some n's. So it's like only 3 n's or 3n plus 2's. So, but that's very recent. It's like 2 years ago or something.
Okay, so this is Maple package that we wrote to do this. So this is identity finder Maple package that we wrote to explore this. That second package is Frank Garvin's package for cube series manipulation. Any of you who've taken the experimental math course here at Rutgers are quite familiar with Garvin's introduction to Maple. And so we use that. We just use his implementation of Euler's algorithm. Okay, so this is a Maple package written to help find partition identities. So let's see what procedures we have. So the main procedure right now is this explore Capparelli thing. I don't know if you can read it, maybe. Let's see, I don't know, I can view zoom factor. There we go. We can better see what's going on here. So this is a procedure. It takes in a bunch of parameters. So diff-min and diff-max. So that is just the minimum and maximum values that we're going to plug in for that difference. Diff-min and diff-max. Minimum and maximum.
It's very nice of you to call Capparelli. It's very generalized.
Yes.
Yeah, Capparelli's type.
Yes. So that is why I'm using Capparelli. So this is exploring identities of Capparelli type. We also have min-max for the smallest part, and then the min-max for the all of the parameters down in the congruence conditions, and then these variables down here. So I lied a little bit when I said we just kind of caveat to 15 terms or stuff like that. The way that we found is the best way to do this is that you calculate every single possible thing out to maybe n equals 15 or so. And then you quickly kind of check them and see, do these factor into nice product size so far? And if you get, and then most of them will already fail and say, oh, it's not a nice product size. So you can just toss that away. It's never going to, adding on more terms is never going to turn it back into a nice product size. So we can just pitch it out. And then we can go back and check the ones that passed the first test out farther. We also are going to stick in a parameter that says what's the maximum period that we're looking for here, because obviously we're only calculating out, we're calculating out 30 terms. Well, it's going to be periodic with period 30 at, so we do want to enforce some sort of thing here.
You could look it up in the OEIS too. Look up the A sequence.
But we're trying to discover new identities. So if they're new, they're not going to be at OAS yet.
Well, the A's might be.
So let me.
No, it's the next step. You discover something that you hope is new, then you go.
Yeah. So. All of this text here is just basically doing what I just said, and so let me zoom back down to 100%, and so this is what we're going to do. So you can see here we are calculating out 3,800, 3,900 some sides, and so it did the first pass, and now it's doing a second pass, and now it's spitting out all of this output here. That everything up to like 30 terms using our given parameter values. This is what it's saying here. All these conjectured for the time being. I mean, many of them are well known identities. So let's see, we're doing this right now.
So it would be nice to be an interface to the OAS. Then you do escape to Unix, and then supersecret.
Yes. I just use the low-tech method of copy paste. Yes. So these are all, and this is spitting out all of the information you need to know. So you can see that it's giving you all of the parameter values. It's giving you the first 30 terms of the sequence, and it's telling you what the parts you're allowed to use on the product side are. And so, okay, should go a little bit faster.
So Ramanujan came up?
Yeah. So as soon as we...
Is this programmed to give only when the exponents are 0 or 1?
Yes, that is easily modifiable for the time being.
I mean,
that's
what's fletching is that?
Yes, what was flash? So you can certainly do things, changing the exponents to get multicolor identities, for example. That is certainly future work. So, we can.
No, of course. I was just
yes.
curious
So
what these numbers are.
We can do things. So looking up here. So here's the parameter numbers. Here's the first 30 or so terms of the sequence. Level, parts, and product. 1, 3, 5, 7, 9. Okay. So great. We rediscovered Euler. Hooray! And 1, 4, 6, 9, 11, 14. Okay, that should look familiar. That is plus or minus 1 mod 5. So that's Rogers-Ramanujan. Let me just see if I can pick an interesting one out here. So let me do this one right here. So I can just it's just something new. So I can just copy paste into OEIS and this is telling me I found case k equals 3, I equals 1 of Gordon's theorem. So okay, hey, I'm rediscovering Gordon's theorem, and I can promise you that many of the ones that I skipped are also Gordon's theorem, Bressoud theorem, Gordon, stuff like that.
That's the B sequence.
It also says 2 results found.
Well, that's probably because I didn't put in enough. So. A few more terms you can verify for yourself that this is the proper one.
That's the B sequence you're looking up. I was suggesting you also look up the A sequence before you filter out the ones that only have zeros and plus and minus ones.
Okay. We should talk about that after. Yeah. Good comments. Okay, so we can scroll through. You can spend a pleasant afternoon or however many just going through here. Hey, look, right down here. This is. I copy and paste here. If you might have spotted what that is, but let's see, will this be enough terms for it to come up with it? There we go. So this is, if you can translate this into a product size, that is exactly the Capparelli identity of the product size for Capparelli. You can see the reference to.
Oh, so Neil, you put Capparelli's identities in there? Somebody
Scroll down a bit and see who the author is.
So
That's Michael.
Yeah. Okay, so we're rediscovering stuff. Is there anything new in here? And so and when we come down here, so let's see. Copy and paste a bunch of terms. And sorry, the terms don't mention anything in the table. So Neil, this is certainly sometimes I still
Hopefully
need to
you're
get
well
in there.
soon.
Yes, yeah. Hopefully soon, as soon as we get a preprint up. And so we can see here, if you spend a little while staring after I write a routine that spits it out for you, this is 1, 3, 6, 8, 10, 12, 15, 17. This ends up being plus or minus 1, plus or minus 3 mod 9 ends up being our product side. And then if you can decipher this thing here, what this is basically saying is parts at distance 2 have there's difference 3 at distance 2. Ignore the smallest part conditions, they don't come up. And then if parts at distance 1, so consecutive parts are within 1 of each other, their sum has to be 0 mod 3. And so that is something that comes up here. And as it turns out, there's an entire family of them. So right down here, I won't show you, but this one is also not in. This one is also new. So the way to interpret this is that we have. So we still have difference 3 at distance 2, smallest part at least 2, and then the same if consecutive parts are within 1 of each other, their sum is 0 mod 3. And so that's plus or minus 2, plus or minus 3 mod 9. And then down here is plus or minus 3, plus or minus 4 mod 9 is the product side. And the same thing I just said, but replace smallest part 2 with smallest part 3. So on the sum sides you have difference 3 at distance 2. You have, if 2 parts are within 1 of each other, they have to sum to 0 mod 3. And then you have smallest part 1, smallest part 2, smallest part 3. These all come together. And then so work on proving this is an ongoing problem. And then just to wrap it up, let me just note this one in here. This is a kind of interesting one. So the congruence classes, if you stare at long enough, they're 2, 3, 5, and 8 mod 9. And you think about that a little bit. That actually is not symmetric. And it's the first one that we have seen all today that the congruence conditions are not symmetric. And so that's interesting. And here the interesting change is now it's if 2 parts are within 1 of each other, the sum has to be 2 mod 3. So that looks different.
I have a naive question.
Yes.
If you go beyond mod 9, might it become symmetric with a longer length? Have you looked at that? Just curious.
So let's see. Does it?
Only with
Yeah. I don't think it does. I have to think to make sure, but yeah. Okay. There's a couple more I didn't get a chance to show you, and of course, proving this is an ongoing thing. But my time is up. So thank you all for your attention.
Having talked, make the reject answer questions in private. Thank you.
There must be cases where you get false positives.